going on, guys? Welcome back to this video. Today we'll be covering Wireshark. We'll be covering Wireshark from A to Z. So if you want to learn how to use Wireshark, this video is gonna be for you. So what we will be covering in this video. First thing, we're going to cover the GUI navigation items. Then we will be covering the packet dissection. Plus, we will be covering again the navigation of packets, how to navigate through different sorts of packets. Also, we will be talking about the data extraction and export. Plus export. They're technically the same thing. And then we will be covering the most important aspect of Wireshark, which is the packet filtering. Okay, so first let's go over the GUI interface and talk about the various sections of Wireshark. So as a reminder, guys, this video is part of two rooms. The first one is Wireshark, the basics, and the other one is packet operations. Okay, so once we open Wireshark, we see this landing page, or we see this interface. So as you can see, guys, here we have the menu. And then we have what is called the toolbar. So the menu plus this bar, both they are called the toolbar. And the toolbar contains multiple, as you can see, multiple menus, shortcuts for packet sniffing and processing, including this button. So you can start live packet capture. And then we have the display filter. This filter is called a display filter. Here where we apply the queries and the filtering. We'll be covering this later on. And then, as you can see, guys, here we have the recent files that have been opened by Wireshark. These represent the packet capture files. And then we have the capture filter and interfaces. This represents the available interfaces and capture points. And lastly, at the very bottom, we have the status bar. The status bar contains the number of packets, the profile, and the tool status. Okay, now let's first start and load a sample packet capture. We can do so by using the file menu, using the open, and then we can navigate to the file. We're going to choose the exercise, the first one, and here we can see the packets are loaded. All right, so as you can see, we have the file name called exercise.pcap. And this represents the packet list. These are the packets that we have here. This pane is called the packet list. Down here on the left, we have the packet details. And on the right, we have the packet bytes. Okay, so the packet list here contains a summary of the packets. As you can see, we can see the source, destination, IP addresses, the protocol, the length. We can, of course, add columns. We're going to see how we add columns to this list later on. Okay, now the packet details on the left pane. Here we can see detailed protocol breakdown of every single packet. Whenever we highlight a packet from the packet list, we can see the information changes in the packet details. We can see the information broken down based on the protocol. Now, on the right, we have the packet bytes pane. We can see the hex and ASCII representation of the selected packet. When we change the packet, the representation here changes. It contains the details in both hex and ASCII format. Now, one more thing about Wireshark is the colors. So we can control the coloring of packets from the view menu. Clicking on view, and then we can go to coloring rules. Here we can see the current rules followed by default to color the packets. For example, we have the R packets with this color, and we have the TCP reset packets in a red color. We can change these colors from here. Okay, now these buttons here represent the packet capturing. If we click on this shark button, the blue button, we will start packet capture, meaning we will start to sniff the packets on the configured interface. Now by default, we will see the interface in here. So if you click on that, as you can see, could run user, yeah, we need permissions, but when this starts, we will start capturing the packets. Let's go back to the exercise. And once this starts, as you can see, we have this red button here. When we click on this button, we will stop the capture. Okay, let's go back to exercise. And then we will go to statistics and we click on capture file properties. Here we can see all the details about the current capture file we have. For example, we can extract the number of bytes. If you go to statistics section, we can see the number of bytes captured and the percentage, the time span, everything there is to see about the current capture file in a brief fashion. We can see all of them here from the stats, captured file properties. Now, let's take a sample packet and go over the various sections on the left pane. As an analyst or even as a network administrator, you need to understand the meaning of every single section from the packet details list. For example, let's take a look at this one. We have the protocol breakdown. First thing, we have the frame. If we click on a frame and collapse, we can see the details on here. Now, the frame here will show us the frame or the packet we are looking at and details specific or pertinent to the physical layer of the OZ model. All this information are pertinent to the physical layer of the OZ model. The physical layer, not the data link layer. Here we can see information about the frame. And then we have the Ethernet. We click on this and here we can see information pertinent to the data link layer, meaning we can see the source and destination MAC addresses of the packets. And third one, we have the Internet Protocol version 4. Here we can see breakdown based on the network layer. We can see information about the IPv4 addresses, meaning the source and destination IP addresses. We can see them from here. As you can see, this is the source address and this is destination IP address. Okay, and lastly, we have information about the transmission control layer. Here we can see information about the TCP layer, such as the port number, source and destination port numbers. Now, sometimes if you're examining a packet that has application layer details such as HTTP, you will see additional section in here. As you can see, this section is pertinent to the application layer of the OZ model. Here you can see information about the protocol belonging to this layer in the OZ model. As you can see, guys, the packet list here details information about every single packet based on the OZ model. So if you don't know the OZ model, it's very recommended, guys, to go back and review it, because everything mentioned here, the protocol breakdown, is heavily reliant on the OZ model. Let's go back to the HTTP layer packet. Here we can see additional entry detailing the protocol in the application layer. If we collapse this, we can see information such as the type of the request, the host, the user agent, meaning we can see details about the as you can see again, the GET request, whether it is GET or POST or PUT or DELETE. We can see information about or details about the application layer protocol from here. Now I understand the details or the protocol breakdown. Let's now learn how to navigate through these packets. So as you can see, guys, these are the packets and there is no here, meaning these packets are numbered. So as you can see, it starts with 1, 2, 3, 4, 5. This makes it easy for us as analysts and network administrators to navigate through packets. But how? So how to navigate through these packets? We go to the Go menu and select Go to Packet. And as you can see, new bar has popped up where we can enter the packet number. Say I want to navigate to the packet number 50. I enter 50 here and I go to the packet. It was 50, so the 0 wasn't typed. 50, and directly it takes me to packet 50, as you can see here. And from here I can again examine the protocol breakdown of this packet. Alternatively, guys, if you want to find the packets in another way, in a more detailed fashion, you can select the edit menu and then go to find packet. So we have now a new bar popped up. We have packet details and packet bytes and packet list. We explained these earlier. So as a reminder, the packet list is here. The packet details is this one on the left pane, and packet bytes is on the right pane. So here we select, or we choose where to look. What is the view that we want to look in? So if you select packet details, it's going to look for the packets from here on the left pane. All right, so here we choose the type of search. It's going to be, are we going to be searching for string? Are we going to be searching for hex value, display filter, or regular expression? Most of the time, the searches are conducted using either string or regular expression. For example, let's select search using a string and type here download and click on find. So what does that mean? It means Wireshark now will look for the string packet, okay, across all packets using the packet details. So if there is a match, it will show me the match here in the packet details. As you can see, we have one hit on packet number 31,192, and we found the word download in here. So it was found under the line-based text data in this packet. If we look closely at this packet, we can see it is a response to a request. You can click find one more time, and you can see more occurrences of the same word. Currently we have only one. So when we have more than one occurrence, as you can see, the packet number changes, meaning now we are examining a different packet that contains the word download. Okay, now let's say you are examining a capture such as this one, and you found a packet of interest. Say you want to analyze this packet, but currently you have other things in hand that you are analyzing. So if you want to get back to this later, what you want to do, you want to highlight the packets. So you highlight this and click on mark or unmark. This will highlight the packets, as you can see, with black color. Again, guys, you can change the coloring rules by going back to file, view, and change the coloring rules. If you want the marked packets to be highlighted using a different color, so you're gonna change the coloring rules. So for now, you can highlight the packets. As you can see, we highlighted them. Then we can get back to them later for future analysis. If you want to remove the mark, you can simply right click and select unmark. You can unmark all the packets. Another useful feature in Wireshark is, suppose that more than one analyst or more than one network administrator working on the packet capture. So you want to see other analyst perspective on a certain packet, you can right click here and select the packet comments. It's going to show you all the comments, if any, that have been written by the other analysts. If you want to write a comment for other analysts to examine, you can write your own here, demo. And if you want, you can write the date and click on OK. Now, if we examine the packet one more time, we can see we have packet comment new section opened up in the details, or in the packet details, where it shows me the comments written. So I wrote the date here so that analysts know when I typed the comment. Okay, so now we know the basic features here. Let's say we want to extract a specified packet for further analysis. Remember that Wireshark is not the only tool in the market for packet analysis. We have T-Shark, we have TCP dump, we have Zeek, we have Brim. We talked about all of these in the previous videos. Now let's say we want to export specific packets for further analysis using different tools. What we can do here, we can select a packet such as this one. We can select it with the control, and then we go to file and say we want to export specified packets. Click on that, and here we can select to export all packets or selected packets only, or we can choose by range using the numbers. Once we do that, we give it a name and we click on save. It will export the selected packets in a PCAP file where you can analyze them later or export them into a different tool. Alternatively, you can export all packets, but since you have the packet capture, you don't need to go on this option. All right, let's go click on cancel. Now let's learn how we can extract artifacts from the packets, such as images, executable files, HTML files, so on and so forth. We can do that using the export objects feature from here. So export objects, we click on this, we can see we have HTTP, exporting artifacts from the HTTP protocol, SMB, TFTP, and other protocols. If you click on HTTP, it will show you all the artifacts that can be extracted from HTTP packets in the current capture file. We can see we have one HTML file, another one here, and we have what looks like a text file. It's a node file, and we have also, looks like we have images as well. We can save all, or we can save a selected one by clicking on save. So we're gonna need to save one of these, which is the text file. You're gonna find the reason later on. So this is the note. We're gonna select this one and save it. Select desktop. Let's take a look at the file. So this is a node file. Okay, back to Wireshark. One more thing which is useful for network administrators who troubleshoot network problems is the expert information. Now, expert information can be found by clicking on, as you can see, the lower left bottom section. We click on this and we bring up this menu here. Now, what all of this means. So as you can see, we have colored different colors. So every color has different meaning. For example, packets with red color means we have problems with these packets, meaning they are malformed packets. We can see the explanation using the group here. So for every color, we have the number of packets. So for red colors, we have 2, as you can see, 15 packets with red color, meaning we have 15 packets or considered as malformed packets. We have, as you can see, 1,636 packets highlighted with the yellow color, meaning we have warnings like error codes or problem statements. And here, this color, it means that we have events such as application error codes, and the blue color is for informational, meaning nothing wrong with the packets. It's just information on usual workflow. So we can use these expert information to analyze the packets and see if we have network problems, error codes, or problem statements. Now let's talk about filtering packets, which is the most important feature in Wireshark. Okay, when we talk about packet filtering, we are talking about narrowing down the search to a different aspect of a single packet or multiple aspects. So as you can see, every packet we have source IP, destination IP, and we saw the protocol breakdown in the packet details list. or the packet details pane. Now, there are different types of filtering. There is the first one, it is called apply as filter. Apply as filter is a way of filtering only a specific entity from a packet. Alright, let's say we have this packet with source IP address that starts with 145.254.160.237. Say I want to search with this IP address. I want to extract all packets or filter all packets with this IP address. I can right click and go to apply as filter. Select it. As you can see now, everything changed. So the number of packets changed, the view has changed, and we can see in the display filter here bar that Wireshark has automatically typed the filter for us. There is no need for us to know the syntax for this kind of filter. But on the other hand, we can see we are searching with only a specific IP address. So here we are looking to extract all the packets that has this IP address as a source or destination IP address. Again, if you want to cancel the filter, we can click on the X button. And this will bring back the original view. Now there is another sort of filtering called the conversation filter. So previously we had only one single entity by which we searched the packets. Now, if you want to, for example, use the conversation filter, we can go ahead and click on conversation filter. And we can choose to look for packets that are similar to this packet or related to this packet in terms of the IP addresses and port numbers. You can right click here and select conversation filter and select IPv4, for example. So look at the filter now. IP address equal to 145 and IP address equal to 65. So why Wireshark brought up this filter? Because when we use conversation filter, we use more than one entity to look through the packets. That's the main difference between conversation filter and apply as a filter. In apply as a filter, we use a single entity from here. But with conversation filter, we use both entities, IP addresses, to look for packets similar to this one. We can also cancel this one and change the way we apply the conversation filter. You can right click here and choose back the conversation filter, and we search with TCP. So what happened here? Right now we are using the IP addresses and port numbers to find relevant packets or similar packets to this one. So here we're looking for relevancy. We want to find relevant packets to the selected one. One more thing about the conversation filter is the ability to colorize the packets. For example, I can right click here and colorize the conversation. Select TCP and I can choose a color for this. So now the colors have changed accordingly. I can right click back and select colorize conversation and choose a different color. This will change the colors. Okay, let's now click on X and choose a different filter. Now there is the filter that's named prepared as filter. So prepared as filter is similar to apply as filter we saw previously. However, the model doesn't apply the filters after the choice. Meaning, let's take an example. So we go here and prepared as filter. Look at this. So Wireshark has, as you can see, automatically typed the filter, but didn't apply the filter yet. So when we enter, we're applying the filter now. It is same as apply as filter. That's the difference. The difference is in prepare as filter, we don't apply the filter. I mean, Wireshark doesn't automatically apply the filter. It just types the filter in the display filter bar. Now, another one is apply as column. Apply as column is kind of different than the previous filters. It adds the relevant selected filter as a column. For example, we can go here to a sample packet, DNS1, select the user datagram protocol, for example, and add the source port here, right click, and we can select apply as column. So now the source port has been added as a column. Back here we can add it destination column as well, and we have the destination column added here. The cool thing is it applies to all the packets, so we can see here the source and destination port for all the other packets, and we can use them as a search criteria as well. Additional feature in Wireshark is viewing the raw data of every single packet. This feature is tremendously used by security analysts and network administrators while analyzing packet captures. For example, we can right click a packet here and select follow TCP stream or follow the stream. It may differ from TCP to UDP depending on the type of packet. Here it is offering only follow TCP stream. So we're going to go to follow TCP stream. We can see the raw details of the packets. So the GET request, everything in red is request sent by the client, and in blue the response sent by the server. And explain these filters. Open a new page. So we're going to start first with the operators that we need to learn before we start learning how to write the filters. We have first the comparison operators. So what are the comparison operators that can be used in the queries? So A, we have the equal. The equal can be represented by two equal signs, similar to Brim, that we have talked about in the previous video. For example, we can search, an example really can be IP dot address equal to 10 10 10 1. Here we're going to use this query to look for packets containing this IP address. So here that's the equal operator. B, we have the not equal, can be highlighted or used using this expression. The same applies here. If you apply this here, it can look for packets where this IP address is not found. C, we have greater than. This is simple. We have less than, and this is also simple. That's the expression. E and F, here we can find greater than and less than or equal, greater than or equal. This is the expression for this. Okay, these are the comparison operators. What about other kind of operators, such as the logical operators? You can open a new page here. And two, we have the logical operators. What are the logical operators or expressions? First one, we have the and we have or, and we have the not. Okay, and can be represented by double ampersand. Now for or, 2 pipes, and for not, 1 exclamation mark. For example, let's say I want to search for the packets containing 2 IP addresses. Let's say IP.source equal to 10 10 10 1 and IP.destination equal 10 10 10 2. Here I want to look for packets where the source IP equals to this and destination IP equals to this. Now the and here will match the condition if both operands here, the one on the left and the one on the right, are matched or satisfies the condition. Meaning if one of them wasn't found in the packets, meaning if the IP address here is 10.10.10.1 was found in one packet as a source address, but the destination address of this packet was different than this one, it's not going to give you, or it's not going to satisfy the condition. Hence, it's not going to return this packet as a packet that satisfies the condition. Now for the OR, the same. The OR works differently in that only one of these operands needs to satisfy the condition, needs to exist in the packet in order to return the packet as a packet that satisfies the condition. And lastly, we have the NOT. An example of NOT is, for example, IP address, ip.source, not equal to this. This will find all the packets where the IP address here is not mentioned. Now, one note about this. The use of this is deprecated. Therefore, we cannot use it anymore in newer versions of Wireshark. So what's the alternative? Instead of using this formula here, we can use question mark, exclamation mark, and here the IP address. Here, it's going to look for all the packets where this IP is non-existent. Okay, now let's take a look at some filters I have here. Let's take a look at this one. For example, this one, we show the packets containing the IP address here. Another one here, this one is deprecated, so we're going to remove this and use the newer expression. Here it will look for the packets where the IP address 192.168.1.1 doesn't exist. Another one example is here. He used the ampersand, double ampersand, because we want to show packets containing both IP addresses. This one here, we look for subnets. Show all packets containing IP addresses from this subnet. Let's take a look at one that's different. Here we look using the source port, using the TCP protocol, TCP protocol.source port, meaning we want to look for packets where the source port of the TCP protocol equals to 1234. Here we search using the HTTP response code. There are so many Wireshark filters, depending on the protocol and depending on many other factors. You can't memorize all of them. That's why it's important to understand only the syntax, the operators, the comparison operators, and the logical operators. Here we can, as you can see, guys, we are searching the packets containing the, first off, we search HTTP packets, and then we search the ones where the response code equal to 200. Here we search within the request method. Here we search within the response code. Similarly, we can search using the protocol name, SMTP or DNS. This one here, DNS.flags.response equal to 0. Here we look to show the DNS requests. Similarly, if we want to show the DNS responses, we're going to replace 0 with 1. These are the TCP port filters. If you want to filter packets using the TCP protocol, you can use these filters: port, destination port, source port. Same with UDP. You can also search using the DNS records, the query type. One means we are looking to find DNS queries where the record equals to A, and here we're looking to find text records. It's going to be query type equals to 16. Okay. Now let's talk about advanced filtering. So there are more advanced filters that we need to know in order to use the filters more efficiently and extract more insights from the packets. We have this filter. Filter name is contains. Let's have an example. Let's say I write this filter http.server and then the word contains come here, and here that's the word I am looking for. So what does that mean? It means I want to search the HTTP packets first, okay, where the server section from the packet equals to Apache or contains the word Apache. It will list me all the HTTP packets where the server name contains the word Apache. Here it means I'm looking for the packets containing responses or packets containing the server as Apache. Another advanced filter is the match or matches. Wait. Let's take an example. Everything is best demonstrated with an example. So http.host. Okay, matches comes here, and then two double quotes PHP, and then here we have say HTML. Okay, what does this filter do? First, again, we list the HTTP packets, and then we are instructing Wireshark to look at the host section of the HTTP packets. If the host section or the host, the value of the host, match keywords such as PHP or HTML, it's going to return a response. And we have another one. It is named as in. Now I use the in operator here to search inside a specific range or scope. It's very useful if you want to search through a port range. An example is tcp.port, and here comes in, and here we search through a range 80, 443, 80, 80. So here we list all the TCP packets first, okay, where the port field have values either 80, 443 or 8080. So here, as you can see, we use the word in to search using ranges. It is very similar to for loops for I, in, 1, 2, 5, 6 used in bash scripts. So here we go. This is the second part of the Wireshark series. In the first video, we covered the complete tutorial on how to use Wireshark. We covered the basics, and we covered the packet navigation and dissection. Today, we're going to analyze traffic with Wireshark. So let's discuss what do we have today on the agenda. First thing, we're going to see how we can analyze traffic and detect nmap scans. So there we go. We have a typo here. We're gonna correct this. So nmap scans, and we're going to take a look at how to analyze ARP packets, meaning we want to take a look at how attackers can perform ARP poisoning and man-in-the-middle attack. How can we detect this using Wireshark? So ARP poisoning plus MITM. They are closely connected actually. ARP poisoning and MITM. You need to, in order to conduct man-in-the-middle attack, you need, as a precursor, you need to perform ARP poisoning. So they are like ARP poisoning, and then you have MITM. And third on the agenda, we're gonna analyze the HCP, NetBIOS, and we're going to analyze KPros. We're going to take a look at the examples of these packets. How do they look at in a packet capture file? Additionally, we're going to take a look at DNS and ICMP packets. And of course, we're going to learn how to extract clear text credentials from FTP and HTTP. And lastly, we're going to take a look at how to decrypt HTTPS packets. So that's what we have. Now, this is a packet capture file that represents Nmap or captured Nmap traffic, meaning there was a machine at point in time where someone was scanning this machine with Nmap. So they captured the traffic and gave it to you so that you analyze the packet capture and find out the nature of the Nmap scans performed against the machine. So to find out, we need to rely on what is called the TCP flags. As you know, guys, in Nmap we have TCP three-way handshake, where the client sends a synchronization packet, as seen here in the examples. From packet 1 to 5 we have synchronization packets, and then we have reset acknowledgement, right? So the combination of synchronize, acknowledgement, reset, these flags can be used to filter or extract packets that would show Nmap or Nmap attempts. So to do that, we're gonna use this filter, TCP.flags. Okay, we're gonna use the TCP flags filter and synchronize equal to 1. So when the synchronized flag equals to 1, meaning we have a TCP connect scan combined with another condition. The other condition is that the server would need to send an acknowledgement scan. Okay, a TCP connect scan, the client sends a hello with the synchronized flag set, okay, and the server replies with acknowledgement. So the other condition for a TCP connect scan to be successful is TCP.flags.acknowledgement needs to be 0. Okay, and the last condition, the window size, TCP.window size needs to be less than or more than 1024. So TCP window size, we have a problem in this. So here it is not Windows, it is window. So here we have 3 conditions. We use them in one filter. The sync flag needs to be 1, the acknowledgement flag needs to be 0, and the window size needs to be more than 1024. So execute this filter, and here, as you can see, guys, Wireshark has extracted all of the packets that would indicate there was a TCP connect scan. As you can see, we see here a synchronized packet sent from this client with the IP address of 10.10.67 to the destination IP address represented by 10.10.47.123. So all of these are synchronization packets indicating that there is indeed an Nmap scan. The number of packets displayed here is 1000. At the bottom here, as you can see, guys, where hovering over with the mouse, the number of packets is 6544, out of which we have displayed packets that represent the filter we have just executed. So if we filter the TCP traffic now, where the port equal to 80, we use the filter TCP.port equal to 80. Take a look at the nature of the packets. Okay, as you can see here, guys, to find out the type of Nmap scan that's used to reveal to port 80, we're going to take a look at the flow of the packets. The first packet, as you can see, we have a synchronization flag set, and then the host or the destination address ends with 123, replies with another packet where the acknowledgement flag is sent, and then the client send an acknowledgement flag, and lastly the server sends reset acknowledgement indicating that that the three-way handshake is finished successfully. So this is typical of a TCP connect scan, a regular TCP connect scan, as opposed to TCP stealth scan. In a TCP stealth scan, the client only sends a synchronization, a packet, and then would never send an acknowledgement. That's the difference between TCP Connect and TCP Stealth Scan. Get the help or use ICMP filters, because UDP scans use ICMP packets. So we're going to use ICMP.type equal 3, that's the opcode, and ICMP.code equal 3. So this indicates that we are looking for UDP scans where the port was closed. And we have 1083. We're going to use this filter. As you can see, we have 138 packets. Now, to take a look at the source machine that is conducting the attack, we're going to have to take a look at an example packet. Take a look at this one, for example, and we scroll down to the address resolution protocol, expand this, and from here we can highlight the sender MAC address. It starts with 00 and ends with P4. This indicates, or this shows, the MAC address of the attacker that has crafted these ARP poisoning packets. Okay, what's next? Next, we need to find out how many requests the attacker has sent. So we're not only looking at the total number of ARP poisoning packets, we want only to take a look at the requests. To do that, we're going to have to use a filter that uses the attacker MAC address. To do that, we're going to have to use ethernet.destination. No, source, sorry. So source, since it is the machine making the request, it's going to be the source. 000C29E2 B4. So that is the source MAC address of the attacker. And we're going to use another filter. Since we want to take a look at the ARP requests, we're going to use ARP, and then the option will be opcode. There are many opcodes that would indicate different meanings. So an opcode of 1 meaning an ARP request. An opcode of maybe 2 would mean an ARP response. So here, as you can see, this is the final filter. We click enter, and we can see we have 284 packets. Next thing, what is the number of HTTP packets received by the attacker? Now, this is easy because here we have the address or the MAC address of the attacker. Now the attacker is on the recipient side, so this will be the destination. And we're going to use on the other side of the condition here, we're going to use HTTP because we want to filter for HTTP traffic. This will list all the HTTP packets where the recipient is the attacker. So we enter and we see these packets. So we have 90 packets. Next thing, what is the number of sniffed username and password entries? So since we are taking a look at the HTTP packets, there is a high chance since we're taking a look at the HTTP packets in here, there could be chances or there could be packets that contain username and password entries. So we're going to take a look at one example packet. So this one represents a GET request to a page or to a login page, login, as you can see here. And there is a response from the server. So if we follow the stream of this packet, we're going to be able to take a look at the raw data. So following the TCP stream, this is the request, and this is the response. Scrolling down, you can take a look at the body of the request. From the body of the request, we should be able to extract plain text credentials. So this is the TCP stream. I'm going to have to go back. Exactly, that's what I need. And take a look at the HTTP stream. So here follow HTTP stream, and from here we see the response of the server. From here, if we search for a combination of username and password, okay, so if we search for maybe username, as you can see, we have the username and password submitted in the form, but we cannot see the actual values. To be able to see the actual values, we're going to have to, make the filter more narrowed. So going to modify the filter. So here, as you can see, the request is made to this host, and this is the web page, and it is a GET request. Usually the credentials are revealed or are sent to the server using a POST request. So you're gonna have to filter the HTTP traffic for a POST request, and we're gonna use this host as another filter. So we're gonna copy this, go back, and from here http.host equal to this host, okay, and http.request.method equal to post. So in this filter, we are using the HTTP traffic, HTTP filter. As part of the HTTP options or the attributes that can be used with the filter, we have the host. We can filter by the request method. So we're filtering for the packets that are sent or that have the host in the packet equals to this host, and the request method equals to post. Now, of course, you can change this to get, to delete, to put, depending on the kind of request you're looking for. Hit enter, and this would reveal all of the post requests. So you have a post request here to user info, and the following packets are all representing a post request to the web page. Let's take a look at an example. Follow the stream, and we scroll down here. We want to see patterns, username and password. Let's use a filter, username, or maybe pass. Okay. So we have one username equal test and password equal to test. Host name of every single machine is transferred through the packets when the client or when there is DHCP, NetBIOS, or KPros protocol in the traffic. So most probably, if we're gonna search with this host name, we're gonna be able to find it in these packets, okay, because they are DHCP or NetBIOS traffic. So we're gonna use the search feature. So edit and find packet. We explained this previously in the previous video. So for the packet details, we're going to keep this as is. We're going to use string search and type Galaxy A30. We search with this, click on find. No packet contained that string in its dissected display. Oh, that is strange. Let's make sure we open the right file. Go to statistics, captured file properties. You can see we opened the right file that represent the NetBIOS and the DHCP traffic, yet we seem to get only the R packets. Alright, okay, let's do this. DHCP. Okay, we have DHCP traffic, but still we cannot find the Galaxy A30. Let's search for NetBIOS, NBNS, and we have NBNS traffic. Usually, if you want to conduct NetBIOS search, you use NBNS. This would show all of the NetBIOS packets that have been captured. Now we want to extract the registration, NetBIOS registration packets. To do that, we're going to use the flags. NBNS.flags opcode needs to equal to 5. Again, guys, as with all protocols, there are opcodes that indicate the request and response for every single stage. For the NetBIOS, we have, as you can see guys, 5 for the registration. Same with the HCP. Different opcodes for different stages during the life cycle of the request. So for request, we use opcode 3, option 3, and for response, we use 5. For denied request, we use 6. And these can be found here. If you take a look at an example, NetBIOS packet, going to the protocol breakdown, we can see here in the queries, the flags, we have the opcode, as you can see here. Okay, so opcode needs to equal to 5, and we're gonna search with another thing, with the host name Leva LGM. So if you go to the queries here, we can see there is an attribute name. This indicates the host name of the machine that initiated the NetBIOS request. So these are KPros packets. In order to conduct global search with KPros, we can use, let's scroll down, we can use this keyword. This would list all of the KPros packets. Okay. Now, the same thing with every protocol. In order to figure out how to extract attributes from these packets, we're gonna have to take a look at an example packet. We go to KPros, and we can see here the tickets. These are the options or the attributes we can use in the filter. So we have CNAME. This would indicate the host name of the machine and maybe the username of the machine. CNAME string. And we have ticket if you want to filter by tickets. So KPros.CNAME string contains your 5. You can see here, let's make sure that the data is correct. The username is or contains U5. Okay, so CNAME string U5, meaning that this is the correct machine. Alright, so to conduct global search to reveal the ICMP packets, we can use ICMP. Again, as with every protocol, we take a look at an example packet and we scroll down to the packet details. We see what kind of attributes we can use in the search. Data, the sequence numbers, all of these are valid options that can be used in the filter. Same with other protocols. We use DNS and we can find out all of the DNS packets. Alright, so DNS is a very common and popular network protocol. Attackers use this protocol to conduct queries or to send queries to a C2 server, as we learned from the previous videos. So there is a high chance that these packets contain queries sent to C2 server in order to, request commands to be executed on the compromised machine. So we're gonna need to reveal the malicious DNS packets, or the packets that probably were sent to a C2 server. To find this out, we're gonna need to rely on the data length. So a malicious DNS query that's sent to a C2 server usually will look longer than the regular DNS query that's sent to a regular domain. To find this out, we're gonna need to use query attribute and name dot length. Gonna need to be more than 15, and we need to also satisfy this condition. Here we're gonna again need to take a look at the payload data. We have a lot of queries here. So there is a malicious domain. You might probably need to take a look at many packets to find the correct answer. If you take a look at the payload data here, we need to find out a unique domain name. That's not so common. So keeping an eye on the payload data here, scrolling down, we can see this one, packet number 2621, and on the payload data section we see a domain name that equals to xfil.com. So that's the malicious domain. Here we go. Now I have FTP packets. Again, we can filter the FTP packets using the FTP filter. We can see all of the FTP packets. Same with other protocols. There are options, attributes that can be used, as you can see guys, to filter for FTP requests, FTP response, failed login attempts, successful login attempts. Every packet has a response code. You can find it from here. From the protocol breakdown, you can see the response code attribute. It can be used in the query, as we have demonstrated with every other protocol. Okay, so ftp.response and then .code has to be 530, indicating a failed login attempts. How many of them? 737. So this is the pane, or this is the packet list of HTTP packets. Again, we can use HTTP to conduct global search of the HTTP packets. Now, usually guys, if you want to analyze malicious packets or malicious traffic sent over HTTP, one of the common signs is the user agent. So a malicious user agent is usually found through packets sent from the attackers. An example packet, we go to the protocol breakdown, and from here we can analyze the user agent. The user agent here is Mozilla. That's not a malicious user agent. Usually it can be malicious. You cannot rule it out unless you analyze it more in depth. Take a look at another one. So take a look at this one. The user agent here is SQL map. Most definitely this is an indicator that an attacker is using SQL map to analyze the web application for SQL injection vulnerabilities. So upon analyzing, or when you analyze most of the packets, you will be able to come up with the list of the user agents used and to attack the host. So basically, let's see here in HTTP, we can extract them, or we can use this filter. So this filter here, you can analyze it. Okay, so here we're looking for the user agent attribute. So this filter will list all of the packets where the user agent equals to SQL map or nmap or wfuzz or nicto. So we have 24 packets. We're gonna have to add this as a column. So apply as a column, and now we have the user agent here. Another filter for the user agent can be this. So here would indicate that there is a log4j attack carrying this user agent, and we can see another one. This is the user agent used. This would now make them 3 user agents. And again guys, we can use another query. Let's go back. Look at this one. We have a base 64 here. If you take a look at this, gonna copy that, copy the value, and go to CyberChef. From base 64, and this base 64 command is used to retrieve a file from the server, lh. It's a bash script, and it downloads the script, gives it execution permissions, and execute on the machine. Look at this one. So that's the user. That's an indicator of another attack was taking place. You can conduct a global search for HTTPS data using HTTPS. Nope. SSDB. Well, it works partially. Maybe you can try with HTTP2. Okay, so why this doesn't work? Why we cannot filter all the HTTPS traffic? Because usually traffic sent over HTTPS is encrypted, which means we cannot have full visibility on the details, including the payload section or the payload data, other data such as the information transferred over the protocol. So we don't have full visibility over what data is being transferred when we analyze HTTPS. So that's why, in order to correctly analyze or to be able to have as much information as possible from the encrypted traffic, we're going to rely on the what's called the TLS handshake. The TLS handshake is the same as TCP handshake, but encrypted with the TLS protocol. As you can see here, guys, there are many states for the TLS handshake. So as you can see, a handshake, TLS handshake type 1, okay, and TLS handshake type 2. So type 1, when a client says hello to the server, and type 2 when the server says hello to the client. We can use these as well to extract the communication between the client and the server over the TLS or over HTTPS protocol. We can see these are requests from the client to the server. And if we use this filter, actually we only change one with two, we can see the server answers to the client, right? So this way we can filter HTTPS traffic relying on the TLS handshake. The question here is, what is the frame number of the client hello message sent to accounts Google? So you're gonna have to filter with the packets sent from the client. Okay, so look here, for example, this one, as you can see in the payload data section, we can see this accounts google.com. Now to be able to find the frame number, we're going to have to look at the packet details. This is an encrypted traffic. To be able to decrypt it, the only way is to have the correct public and private key. We have to make sure that we have the keys used to encrypt the session. As you know, guys, when you browse a website using HTTPS, as you can see in the browser here, there is a session open between you as the client and the other website or the server as the server side. This session, okay, uses pair of keys. If we cannot capture these keys, we're not going to be able to decrypt the traffic. Okay, so to decrypt the traffic, we're gonna X on this, go to File, Edit, Preferences, and then go to Protocols. Gonna supply Wireshark with the correct keys. So let's see here, looking for the correct protocol. It's gonna be long, no. So TLS is ready here, okay. And here the pre-shared key is what we need. The file contains the encrypted or the encryption keys. Okay, so we browse to the keylog file, we already have it here. Gonna open and then click on OK. So now provide Wireshark with the correct keys to decrypt the traffic. Next is to type HTTP 2, not 1 man, 2. Okay, and now we have the traffic decrypted. Now we can take a look at the packets in clear text. Okay, so go to Tools, Credentials, and Wireshark automatically extracts all clear text credentials transferred over non-secure protocols such as FTP and HTTP. You can see them in here, the username and additional information. Let's take a look at this one. See, we are brought to the packet number 170, and we can see that there is no password provided, empty password. So, assumingly, you have a PCAP file where an attack has happened. You have to build a hypothesis. What is the kind of attack? What is the vulnerability? What is the exploit? What are the indicators of compromise? So you can build a story of what has happened by just finding the indicators of compromise. All you have to do is to spot the anomalies. So as you can see, we have OpenVPN traffic, and we have DC ERPC, right? You have EPM, RPC net logon. We have something weird happening. So let's go down. We have SMP v2, as you can see. So assumingly we have an attack here, so we have to find out what is it. So let's see here. So as you can see, we have this IP address, initiating requests with SSDP. Let's go down, see more. Oh, we see a repeated pattern. The repeated pattern is the IP address is 128.68.128. As you can see, is initiating request with this protocol. And also EPM TCP. Let's filter for this IP address. IP.adr equal 192. You see all the requests coming through to and from this IP address. So we see DCERPC. Okay, let's now get the help of Google and see what is that. What is this protocol? Is it an indicator of compromise, of some malware we don't know, or of some attack that we don't know of? DCERPC. What is that? So DCERPC is a specification for a remote procedure call mechanism that defines both APIs and over-the-network protocol. We'll listen for incoming calls. A client will call this endpoint mapper and ask for a specific interface. So we have RPC requests here going on. Okay, EPM. Let's see what is EPM. Endpoint mapper. This is the endpoint mapper for the DCE RPC. So it's connected with this protocol. And an integral part of it. A client will call the endpoint mapper at the server to ask for well-known service. So they are tied together. So we can just conclude that this IP address is doing remote procedure calls or maybe RPC enumeration. So we can just now take the first hint that an Active Directory attack was happening. An Active Directory attack, RPC is used to enumerate more information about the server or the domain controller. TCP traffic, again, DCERPC, RPC net log on. Let's expand the details of this packet here. So this is the first packet where the 28th is initiating RPC logon to .6. Microsoft Network log on. Computer name DC01. Computer name DC01. Maximum count. So what is the source? Okay. Let's see information about the distributed computing environment. Version 5, packet this request. Okay, let's see the reply now. So it seems like the 28 IP address is trying to log into 1.6, right, which is the DC01 computer, by the way. And now let's see the response by the DC01. Let's have a challenge, success. So after the RPC enumeration, as you can see here, assumingly the attacker has been able to log in successfully to the DC01 computer. Now after that, TCP, RPC net login, again they logged in again, and we have RPC calls. Let's go back, down, 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 down. These are all the same. backup domain controller. Let's look at this log and packet again. TC01. Yeah. Okay. Let's see here. More packets. So we have here SMP. Again, the IP address 128 is doing SMP request. Let's see the details. SMP server message block details, SMP header, negotiate protocols, status success. Okay. SMP v2. Let's hit the header. Status success, signature ID. So it could be one of two scenarios. The owner of this IP address is doing enumeration of the shares on the network or on the computer that ends with 0.6, which happens to be the domain controller, DC01, or it could be that they're doing SMB attack, like WinRM SMB to brute force the username and password. But this is not, I don't think this is the case because it would be shown here. It could be that they are enumerating the shares or they are using secret dump to dump the username and password of the shares. Let's see more packets. This is TCP, SMBv2. Command negotiate protocol, and then we have the response success from the host. And all of the, let's see the remaining packets. All the remaining packets follow the same pattern. Request, and then they return the success. Request, success, response. And then we have this DRS UPI1. Let's see what is that. DRS UPI1. Microsoft Directory Application Service. Directory application. So this is the first request. Let's filter for this. DRS UPI1, DRS UPI1, UPI, UAPI. The first request, as you can see here, this is the first request. Let's see the details. Encrypted data, DS bind. Okay. More packets. The last packet is this one, also SMB, but the response code was TCP. And then the remaining packets are OpenVPN. So you can build a hypothesis that there was an attacker who was enumerating an Active Directory machine called DC01. We saw that. They enumerated the RPC protocol and they found information about this domain controller. Then they proceeded to enumerate the shares and possibly dump the username and password or brute force the username and password of the shares. So these patterns follow the zero log on. So since here we are analyzing a compromised web server and we're given a subset of the overall traffic that took place while the web server was compromised, what we need to do here, we need to take a look at the HTTP traffic. We're only interested here in uncovering what has happened before the web server was compromised. So there must be definitely some HTTP traffic, malicious HTTP traffic we can uncover before the web server was compromised, right? So let's head over to Wireshark and now filter with HTTP traffic. So hey HTTP, and now we reveal the HTTP traffic. So the first thing we need to do, guys, here is to find out what is the source IP and the destination IP. Meaning, we want to find out what is the IP address of the attacker and what is that one of the web server. We can find out by looking at the info here. We want to see who is making the first GET request. So if you take a look at this get/HTTP, as you can see, the first GET request stemmed from the IP that ends with 7, and the recipient was the IP that ends with 5. This means that the IP that ends with 5 is the web server, and the IP that ends with 7 is the attacker. Okay, so now we set the IP address of the attacker. Now we know the attacker IP address and we know the web server address. Next, we want to see and take a look at the pattern of the requests that have been sent from the attacker to the web server. The first request is a normal request, right, getting the main page, and as you can see, the web server has responded with not modified, and then the attacker requested to access the image welcome, and then as you can see, the attacker requested to access the upload page, upload.aspx, and after that the attacker, they tried to upload a file, as you can see, from the path post request, and then we have the upload page, and the parameter happens to be named operation, and the operation equals to upload. So as you can see, we started to uncover some of what has happened. So let's go back to the first square and right click, follow the TCP stream. We want to follow the full stream of these packets. So we right click and we select TCP stream. Okay, so we have a series of requests and responses. Here's the request from the attacker, and here's the request from the response from the web server, highlighted with blue. So we see the first request to the main page, and then the request to the to access the image, and here things start to get interesting. So accessing the upload page, and the web server had no problem with that. It returned the upload page. Fine. Scrolling down. Here we see some of what has happened. As we can see, the web server response on that seems to there has to be some form where you can upload the file. As you can see, this is the operation, the parameter, right? And here we see the request type, and here we see also the authentication key. Please specify a file. So when the attacker requested to access the upload page, here the server responded with a page displaying the statement, please specify a file, of course along with an input that takes the attacker's file and upload it. The parameter is operation. Okay, let's see next what happened. Next, the attacker seemed to have provided the file name. As you can see now, the attacker accessed the upload and provided the operation, which is upload. If you scroll down, we can see the file name that has been uploaded. Here it is, file name equals cmd, and here we see also the authentication key is admin. So the attacker seemed to have access to the web server somehow as an admin, judging by the authentication key here. So it is admin. So what happened here, guys, is the attacker has got access to the dashboard of the web server. They might have signed in somehow, but we were not able to see how they did that. And this is it. They uploaded a web shell, but we still don't know how they logged in. Anyway, scrolling down, we see the web server response. As you can see, the web server accepted the file and said file uploaded. Fine. The next thing the attacker did is visiting the CMD and issuing commands. Let's take a look at what are the commands the attacker has issued, so we can see them in the response of the web server. Scrolling all the way down, let's see here. Okay, here is still yet nothing, and then we see post, the post request to access the CMD and issuing the commands. Now here we see the command, guys. Under the path, and then you have the CMD equal to cert utility dash URL cache dash split, and then the attacker seems trying to retrieve a file from their server which ends with .7, if you remember. And what the file they're trying to download, it is the netcut, and they are saving the netcut to user public netcut, and then they run it. Let's see what the web server responded with. If you scroll down, the server said certutil URL cache command completed successfully. So the attacker has retrieved the netcut from their server and downloaded to the victim machine. Okay, now we want to find out if the attacker managed to successfully run the netcut on the web server. We scroll down, see another request from the attacker /cmd, and let's take a look at the command they tried to run. So scrolling down all the way till you find the CMD. So they navigated to the save path, or the location of where they stored the netcut, C users public NC, and they issued NC. The IP is the one that ends with .7, which happens to be the attacker's IP. So they're trying to connect to the attacker's IP, to their own IP, on the port 444 and -e CMD and button equal run. So the attacker has uploaded the web shell, and through the web shell they were able to retrieve netcut and run it on the virtual machine. So now we want to find out what has happened post compromise. So how do we do that? We now know what the port the attacker is using to send and receive commands. So we close this and we go back to the Wireshark filter. So now we know how the hack has happened. The attacker has logged into the web server somehow, maybe through a web vulnerability or through brute force, and then they managed to upload a web shell named CMD. Okay, after uploading the web shell, they were able to retrieve netcut from their machine and issue it on the victim machine to connect back to their machine. So now we want to know what happened post compromised. So we type tcp.port equal 4444. These are all of the packets that were exchanged between the attacker and the web server, or the machine that hosts the web server. Note that, as you can see here, the first packet on this port is actually stemming or coming from the web server machine .5, right? And the reason for that is it is a reverse shell. So in the reverse shell, the first connection comes from the target machine, not your machine. The first connection comes from the target machine, connecting back to your machine, and then you start issuing commands. Now, starting from here, let's right click and follow all the stream to see what has happened post compromise. Okay, so here the attacker has connected to the target machine. It is Microsoft Windows, and we see here the first command they issued is who am I. As you can see, they landed on the machine as the web server user. Then they issued ipconfig to learn the network configuration, which is important in any engagement or any hack. You want to know what are the IP addresses on all the interfaces connected to the machine. And if you scroll down, we see the attacker has cd'd to the home, the main directory C, and they issued PowerShell command. So what does this PowerShell command do? -ap bypass execution policy -c invoke web request, and here they're trying to download a file, as you can see, from their machine that ends with 0.7, and this is the file name. The file name seems to be base 64, no, base 60, base 32, judging by the uppercase characters and the numbers between 2 and 6. And then they saved the output file under users public, and the file name is file.txt. But they got an error. The term invoke web request isn't recognized. That's the response from the machine. And then they did it another way with cert utility. Again, trying to download the file from their machine and storing the file under users public, and this time the system cannot find the path specified. Again, it failed. This is the Wireshark file, and we have a lot of packets to analyze. As you can see, not a lot of packets, but not also a few number of packets. So we have TCP here. As you can see, we have HTTP. Let's filter for HTTP packets, and we have 4. As you can see, we have, take a look at this packet. So someone is trying to retrieve a file called shell.php. So this means that someone has uploaded another shell different from ours, right? If you follow the TCP stream here, get the details of this packet. Okay, then, so you see this is the response from the server. If we scroll down, and this is the path, get FTP shell. Okay. Back to HTTP. What else we have? Get favicon not found, and we have another response from the web server. Let's go back now, see the TCP packets. Now, since we have a lot of TCP packets after the HTTP request to the shell, we're going to need some smart way to analyze these packets and extract the plain text data. Since we're looking for plain text commands, or we're looking for the commands that the attacker may have executed against the machine, we're going to have to do something else. So we're going to go to File and export packet sessions, dissections as plain text. I'm going to save this here, say packet dump, save that, and we're gonna go back and inspect the file. So okay, desktop. There we go to try hack me. Now we have the packet dump. I'm gonna open this with mousepad. Okay. Let's scroll a bit down, more and more. Take a look at this one. Linux startup 4.0 generic. So this is the data being, actually the data here is returned when you ask for the version of the operating system, which means here the attacker has, you know, at that moment they started to execute commands against the system. And right, as you can see, we have dub data. So how about now we look at the frame 45 in the Wireshark file. Since now we have spotted the packet where at which the attacker started to execute commands against the system, we're going to go back to the Wireshark file and look for the frame number 45. So this is it. Follow TCP stream, and yep, here we go. So here is where the attacker managed to get access to the system. As you can see, they executed ls, then ls-la. If you scroll down, they typed who am I, they grabbed TTY, cd home, cd lenny ls, and sudo-l, and here they typed a credential. As you can see, we have SMB2 network capture file, and if you scroll to the negotiation part, so here we have negotiation. It means there is a user trying to log into the SMB server. Now you go to negotiate, go to session setup request. Scroll down to SMB and then to session setup request, security blob, scroll down. So we have got NTLM secure service provider, which means we have the network capture has captured the NTLM hash. So by uncollapsing or collapsing the NTLM response, expanding the NTLM response, we have also NTLM response here. So we have something called NT-proof string, and we have the NTLM v2 response, which means we can just compose an NTLM hash to crack. Of course, we have username, lgreen, hostname, and 3B. So, how to take advantage of everything we have seen so far? So basically, if you are capturing NTLM hash from a captured file, there is a formula to follow if you want to crack the hash. So let me grab my notes. So here is the formula. First, you have got the username. Then, after the username, you have the domain name, which is 3B. Let me make. Okay. So the username, the domain name, and here is the server challenge. How to get the server challenge? Simply go to the negotiate capture and scroll down. Negotiate flags. Hopefully I will find it here. No. Server challenge. Let me check here. So in the session setup response, NTLM SSB challenge, it must be here, I guess. So NTLM server challenge, this is server challenge. You should follow the username and the domain name with the server challenge, and then you put the NTLM challenge. You grab it by going to the packets, the authentication packets. You will see there is, let's see, the NTLM, the proof, NT-proof string, and lastly, you follow it by the NTLM response. The NTLM response is the part that comes after the 22 here. As you can see, the NT-proof string starts with 73 and ends with 22. So you highlight the NTLM v2 response, you just copy the value like that, and you start with the part that comes after 22, 0101, all the way until the end of the string. So this is the formula of the NTLM hash captured from the network capture file. So what you have to do now, you have to put this in a file like you do when you create a hash file. and use hashcat to find the password. So here I have saved I have set snapshot of the work. I don't need to do it again. Let me show it to you. So basically, if you go up, so hashcat, and the mode is 5600 for NTLM. This is the file that will contain your hash, this one. And here we used rockq.txt. If you scroll down, you see the password is password.